So we'll keep going with AOI logic and or invert logic and the stick diagrams. What is this logic? Do you remember? What's this called? Yeah, XOR. Okay. Do you know that if you put a bar or XOR not is XNOR? So what's XNOR logic? Do you know? A, B, or A not, B not. Okay. So this is called XNOR. How do you verify it? Do you remember De Morgan's law? A or B not equals A not and B not. A or B, A and B, sorry, A and B not equals A not or B not. Okay, so you split the bar and change the sign, and they are equal. Here, you split the bar into two bars and change the sign in the middle, and they are equal. That's the way you can remember this, right? So now let's start from here. A, B not, or A not B, that's XOR logic. And if I put a bar on the top, according to De Morgan's law, this equals what? Split the bar and change the sign. Let's start with the top bar first. So split the bar and change the sign, you're getting A and A not B not, right? Okay? And then do it one more time with each of these two. Split the bar, change the sign for this guy. It becomes A not or B not not. And A not not or B not. And that equals, because not not is still itself, right? So B not not is still B. So this becomes A not or B and A or B not. Remove the parentheses or expand it. It becomes A not, so this and this, A, or A not B not, or AB, or B B not. And this is 0, and this is also 0. 0 or something is still that thing, right? So 0 or this, you can directly just remove 0. It's not affecting anything. So eventually this equals A not B not or AB, which is exactly the XNOR logic. Because this is XOR, right? The inverse of XOR equals XNOR. Okay. Now let's look at one example here. It's not exactly the XOR logic, but it's something else. Y equals A not or BC. How to draw the layout of the transistors to make this work in just physically using transistors, okay, using PMOS, just CMOS, PMOS and NMOS to make it work. Remember all these AOI logic or all the gates, or all the transistors. For example, the very basic one, which is an inverter. Okay, so that's A not. For NAND gate, AB, and this becomes AB not. So when we're using this way to design all the circuits using transistors, they're always being inverted. Always has a bar on top. Okay, so in order to design the circuit using transistors in a similar way for this logic, we probably prefer a bar on the top, but we don't have a bar on the top. Can we make it up? Now, if you don't have a bar on top, it's kind of difficult to design a circuit like this, because after you put PMOS on top and NMOS at the bottom, and eventually the logic here will be inverted. It's just the nature of the circuit, okay, and not change it. And remember I think that was probably on Wednesday actually, last week. So we were talking about how to design the circuit using the logic here, right? And with the same methodology by designing the NAND gate and NOR gate with the CMOS transistors. So if you have a AND logic under the bar, you place two PMOSes on the top in parallel and two NMOSes in series at the bottom, remember? Okay, if you have like an OR logic under the bar, you place two PMOSes in series on the top and two NMOSes in parallel at the bottom. So that's the way we do it, okay? For this one, we don't have a bar yet, so let's make up a bar. A not or B, C, let's put two bars on top. So still itself, right? It's going to be inverted by twice. And then we implement the De Morgan's law. We keep the top bar, we're not changing the top bar now. And we split the bar in the middle and change the sign. So we're getting A not not or B C not. Right, and this becomes A or and sorry. Split the bar and change the sign, right? Split the bar into two halves and change the sign from or to and. And this becomes A and B, C, not, not. Yeah. This one? No, you treat this one as a one entity. Then you can do it one more time. I'll do it this time in this step. So it's going to be A and B not or C not, right? Okay. And this becomes A, B not or A C naught. So now you get logic at the bottom of the bar. And now you can start designing the CMOS logic. All right. So what the circuit looks like. You have an AND logic here, but overall it's an OR logic. So which means these two, this block and this block should be in series or in parallel for the PMOS on the top. It's OR logic, right? It's NOR. Yeah, if you in series. So you have one box here, one box here. You don't. So these are the box here is these guys, but you don't worry about that right now. But they should be in series, right? And then you got two boxes at the bottom for the NMOS is in parallel. That's a NOR gate. That's a NOR logic. Okay, and now let's design whatever inside this block. This block. So inside here, it is an AND logic. So AND logic, you need in parallel, right? So it becomes this. That's the first parallel PMOS, and one signal is A, one signal is B naught. Okay, and then in series with another two parallel PMOSes, and one signal is A, one signal is C naught. These are both A's are actually shorted, but let's just leave it there for now. Okay, so we are done with the PMOSes. That's a CMOS logic, so we need an NMOS at the bottom as well. So these two boxes are in parallel, but internally they are in series. So we'll have this. So what are these? And what are these? What are they? What is this one? A, B naught, A, C naught. Okay. And the output here equals A, B naught or A, C naught, naught. Does that make sense?
This is the point of doing all that logic at the top is because it's when you lay out the transistors, it's sort of inherently inverts the entire thing. That's why you want that extra full block on the top.
That's right. Mm-hmm. So that's the nature of the circuit. If you look at the NAND gate and NOR gates, they always do that thing, right? So if you look at the logic, it becomes something and bar. Any questions with this circuit here? So far, we can look at a different logic for the next one. So we did an extra step over here, I think. Is there anything wrong with it? I mean, let's see. Okay, so this is method 1, for example. How many transistors you have over here? Not including the inverter that inverts the logic from B to B now. Let's don't look at that one for now. So you have 8 transistors. right? To implement this logic. So what if we do this? Y equals A not or B C, which equals A not or B C not not. And now we just look at this one. So we just design a CMOS logic with this one, then we add an inverter afterwards. It's going to do the same logic, right? And now let's see which one has less number of transistors. So this one is A naught or, so you still have two blocks in series on the top for the PMOS, but it's just the one transistor for A, and then two in parallel. So this is A, and this is B and C. For the bottom, this block and this block, this should be in parallel, right? And so one is A, one is unlogic, so B and C are in series. Okay. However, the signal here is only A not or B C not. It's not this one. It's the inverse of that one. So what we need to do is have to invert it, right? So this becomes A naught or BC. How many transistors we have in this circuit? Still 8. But it's less integrated. If you do the layout, you'll be able to find out they could be slightly different. The reason for that is we can, when we manually laying out this guy, we can probably just draw one stick. But this guy, you have to do one for this, one stick for this one, then put an inverter afterwards. Just following this guy. Let's try how to make it happen. So A, B, C, 3 transistors. A, B, C, like 3 transistors. You have 1, 2, 3. Looks like they're in series, but you can wiring them up in a different way to make them connect in this way, right? That's what we did last time. Now let's design this a little bit. I drew one stick to make it simple, but now how do we wire it up to make A on the top and then two the B and C in parallel at the bottom of A. So for example, if this is A, that's the power line, introduce the power line to A, the current runs through A channel, and you have to split this point into 2 for B and C, right? So these 2 transistors should be in parallel. So you can do this. Is that correct? Because one point, you introduce the one point. So this is A, power line runs through A transistor, and then getting split. This is still the same voltage node. Just treat this wire and this node as one node. So it's getting split into 2 branches. So it goes through one transistor, another transistor, and then merge. So that's a parallel circuit. So one is B, one is C. Does that make sense? What about the bottom? NOSes. That's the output. That's this joint here, this node, right? So this node getting split into 2 branches. One runs through A. That's A, for example, and go to ground. And another another branch is the two. What's happening? That's the second branch, and these two transistors are series, which is B and C, and then also goes to ground. Okay, so that's the layout for PMOS and NMOSes. And you know that the poly, they should be connected together. Okay, so directly draw a poly from top to bottom and short them together, so it's one signal line, same signal line. Okay. But it's not done yet. We need to add an inverter to it, right? So is there a way that I just add an inverter here and then just use a one stake? It can be very difficult because they are not, so it's a drain of this PMOS, but however, the drain of the PMOS is connected to the gate. So they are not sharing any diffusion, or the P plus. It's connected to the poly. So you can never get just one stick or one line to include this inverter. So I have to draw an inverter here separately. Okay, and this is the output, connect to the input of the inverter, and then that's the overall output. Even though this one has the same number of transistors compared to this one, but it may be more complicated when you manually laying out the circuit. So now let's come back to this one, see if we can do a one-liner, just one line to include all the transistors. Is that possible? One, two, three, four. You need 5 nodes to have 4 transistors. It's a power rail. 2 in parallel and 2 in parallel, and then these 2 in series. How do we do that? I'm just trying, I don't know yet. So let's for example, if we do this, no, see. Like this. So why I get a 1 wire on the top instead of having 2. So let me do it another way, so you'll see why that doesn't work. Okay. So if I introduce 2 power trails from the top and then get a 1 in the middle, so it's 2 parallel transistors, right? And merge. And this node doesn't have any connection with these 2 transistors. It's gonna fail. You know what I mean? Because it's one stick. So this is already connected to the second block. So you cannot introduce the 2 wires and parallel transistor in that way. So I have to do it this way. So 1 wire from the top, and then these 2 are shorted. Okay, and you can use this joint, which is a shared node, which is here, because the one line. So this one shares the source and drain are sharing the same node. Okay, So this node is here, and then you split that node into two, and then you place two transistors in parallel, and then that's the output. Does that make sense? If you do it like this, it's going to fail because it merges to the middle, and the middle doesn't have any connection with the shared joint here. And you do have a shared joint. So I have to do just introduce one line first and then merge it into two, and then use that one and split it into two and merge into one. Okay, for the bottom, that's easier because it's just simply two series transistors in parallel. So just inject the current into the middle, split into two channels or two directions, and have two transistors in series on each direction, in each direction. So after laying out this circuit, you should know which gate should be which signal. Let's take a look at it. You cannot randomly name them because you are hoping that the gate here is the same signal as the gate here. So you can directly just draw a straight line. You know what I mean? You don't want to draw, this is A, let's connect this way, and then let's connect this way. They are going to short to each other. So the best way to do it is this A, B, C, D. You know what I mean? Let's check if this is correct. So I introduced one wire here from the top, from VDD, which is this one, right? That's VDD. Here is VDD. Okay. Coming down, that's power supply. And then getting split into two branches. So A and B naught, they are equivalent. These two signals, these two resistors are interchangeable. So it doesn't have to be like this is A, this is B naught, or this is B naught, this is A. They are interchangeable. But you prefer which one to be A, which one to be B naught, and why? The parallel transistors doesn't matter, they are interchangeable. But the series ones, they are not, because there will be one at the bottom and shorted to the ground. So it's making a difference. They're different, right? It's making a difference here. So because which one is A, which one is B naught? So this is A, right? Okay, so in here, you have a choice. So which one you want to name it as B naught, which one you want to name it as A. They are interchangeable. They're in parallel, right? Parallel transistors are the same. Definitely this is A, this is B naught, right? So you can directly draw a line when you do the layout. That's the gate. Same gate, same signal. What about these two? So this node is this node. Okay, and you draw a line here so you can share the same node. So they are basically the same electric node. No difference if you draw a wire, okay? Just the same metal piece. So this same metal piece here getting split into two branches. One here, one here. Okay, so one must be A, one must be C naught, and they are interchangeable, so it doesn't matter actually. But for here, it matters because of this. C naught is closer to the ground, so this must be C naught. And this must be A. So this must be A, and this must be C naught. When you lay out the circuit, keep in mind, if you don't do that, it's not going to pass NCC. What is the layer of this trace? Metal 1. What is the layer of these ones? Poly. So does this node matter? No. So now the question is, you have 4 signal lines, how to introduce the signal into the polys? You draw a poly here. That's B naught. Can you draw a poly to here? What do you do? Via and metal 1, right?
Is it bad for the inputs on different layers?
No. But eventually you have to use metal 1, even though you use the poly here, but you still have to have a metal 1's node and have a little piece of metal 1 here. Yeah. Yeah. Because you put a node here, or there's a signal input just next to this gate. So you have to make it ready for getting connected to other metal wires. So use metal wires to route all the signals, right? Yeah, same to this one. This is also A, which is interesting. So they're actually basically they're shorted together. But for C, if there's a metal 1 here, you don't have, you cannot just directly draw it here, right? That's a metal 1. So you can just maybe just draw a metal 1 here, okay, like C naught. And then have a metal 2 node if you want. And then introduce the metal 2 to this direction of C naught. Okay. And we find out this is a lot easier than this one when you laid it out. It must be more compact as well because of everything is designed in one line. This one you have to draw another gate next to it to invert it. Getting more complicated. Any questions with the stick diagrams by far? So let's look at more examples. CD actually. Still, we need two bars on the top, and we can actually factor out C and combine these two terms. So it becomes 2 bars, A or B naught or D, C. Let's just keep doing this. I'm not sure if this is eventually making it easier, but let's see what's going to happen. So this becomes split the bar and change the sign, and you're getting A naught and B naught or D, C naught. And this equals A naught and B naught or D naught or C naught. And this becomes A naught and B naught naught and D naught or C naught. Seems like all the effort is trying to get rid of the bar on the B, on top of the B, which is A naught and B, yay. But I got 2 bars on C and D. Let's see if we should, yeah, let's start working on the layout from this point. What about that? Okay, we got a bar on top, which is great. So we're gonna start looking at the logic. So overall, it is unlogic. It's unlogic, which means the PMOS on the top should be in parallel, right? Is that correct? These two should be in parallel to the PMOS. Yeah, it's a NAND gate, right? It's a NAND gate. So you have one for A naught and something for all these rest of the logic. So for the rest, you have 2 blocks in series for these two in series, and these two in parallel. So it becomes BD naught, BD naught, sorry, D naught, BD naught in parallel, and then in series with C naught, and this in parallel, right? For NMOSes, these two are in series, so you need a 1A naught first, and then the rest of the logic at the bottom. And because these two are in series and this is in parallel, OR logic is in parallel. These are in series. So we got C naught in parallel with B and D naught, like that. Is that correct? How to lay this out? Is that possible to use a one-liner to figure out all the PMOSes? I don't know. I didn't lay it out on my notes. Let's take a look at it. So if we have a power line on top, 1, 2, 3, 4 transistors, you need 5 nodes. See if that works. So first I have to get a parallel 2 branches. One runs through A, one runs through the rest. So there's no choice. Let's just draw one line here, okay? Draw one line here, so it's going to run through A, and then the rest. So for the rest, you have 2 transistors in parallel and then in series with another one. So you need this node, output this node to be on the right-hand side, which means it is challenging. Can we still do that? So the problem is if I introduce a line here, right? So I got 2 branches, but I'm getting a middle node over here, which cannot be in series with anything else. So the C will be here, but not being connected to this node, right? So how do I do that? It may not be possible to put everything in one line at all. It's possible. I just don't know. 1, 2, 3, 4, 5. But can we move the transistors around to make it happen? Because these 2 are in series, and they don't have. I don't have to place the 2 transistors on the top. I can place the C0 transistor on the top, and these 2 parallel transistors at the bottom. It's gonna be equivalent, right? It's not changing anything. But then spend more time. So I'm saying the light is tired with C diagrams. Okay. Too difficult for the lights. So what if I swap them? You know, now it's challenging because I have to deal with a parallel transistor first, right? Can we, you know, redesign the circuit to make it look like this? Is it changing the logic or not? Oh, is this changing the circuit or logic? Is it changing the logic for the PMOS? I just swapped these 2. It's not changing the logic. But is this making it easier to lay it out? I don't know. Let's do it one more time. Still doesn't work. You can ask for some refund from the college, probably, for tuition. So first, there's no choice for this guy. Let's just draw one line here, right? So that's going to be A, not. All right. Yeah, it's going to work. It's going to work. And then C naught, and then twin parallel.
So when you're talking about not being able to change the order of elements in series,
You mean here?
no, just like for this bottom portion.
Yeah.
Like when you're laying it out, the what is that? D naught, I guess.
Yeah, D naught.
Going around. It's just so that the layout matches with the other thing.
Mm-hmm.
It's not because it changes the logic.
No.
Okay.
Mm-hmm. Yeah. So you design the circuit by yourself from the logic equation. No one told you have to name this guy as D naught. If they're interchangeable, you can rename it in order to make it match. You can always modify it. But did you see the difference here? So if I design it this way, then I won't be able to put everything in one line. But now I modified it, and now everything is in one line. It saves a lot of space. So this is a process probably have to go through when you design your circuit, manually laying out those transistors. It's just optimizing the layout. So none of the tools like Cadence or other tools can modify the layout this way. So it only happens when you manually lay it out. You can really optimize the space by designing it like this. The VLSI tools, these EDA tools, are not able to optimize the layout, for you in that way. I think so, yeah. If you look at the layout, EDA tools result, the VLSI layout, it's not readable. It's similar to assembly language programming. Like you cannot really understand what's going on just by looking at the machine code. Or no, assembly is also understandable, right? But machine code is not. C and Python, they're just English. That's why it's easier to understand. But assembly is slightly more difficult, but machine code is totally not understandable. If you didn't design or don't have a data sheet on the other side of the table, but looking at like this 101001 represents what, right? Someone designed the hardware to let you use that instruction. If you don't know the hardware, the instruction doesn't make any sense. We just want zeros. Similar to the VLSI layout, if you look at the results from the VLSI to like Cadence, it doesn't make sense at all. It's just that all the sticks, the metal traces are going to anywhere. But when you are looking at the manually laid out circuits, you can actually reverse engineer it. Okay. What about the bottom part here? So this one works, no doubt, right? And are we going to see the same problem as when we designed the circuit over here? Probably not. It might be easier. So let's keep using the same circuit here for the bottom part. That's the output from the top. So it should go through A naught first. And then two transistors in series and one transistor just by itself. Like this. Is that correct? Same node. So this node is this node. Same node. Okay? Being split into two branches. One goes through C naught, one goes through C naught, another one goes through A naught. One goes through, this is just a way. Is that correct? No, that's not. It's not in parallel, right? Sorry. It's in series, not in parallel. Just one line here. So this guy dominates the path here. If this one got shut off, then nothing can go through this bottom transistors. So that was wrong. Okay. So that's A naught. And this node is this node. Can we still do it? Yes. This becomes C naught. And this is B and D naught. Right? So this node, which is output from A naught, which is a drain of A naught, is shorted to the source of source of A naught is shorted to the drain of C naught and B. C and B. okay? And then they're in parallel, right? And merge to one and flow to the ground. Make sense? Is that correct? This one? Take some time to digest this, the way that you design stick diagrams or the layouts. It's slightly more complicated than circuit one wiring. Any questions on this? No? You just need more practice, okay? It's not a big deal. So tomorrow will be the lab in 2771. Continue working on lab 7 or lab 6, the second part of it. So that's a 2-week lab. Okay. So after finished all the labs, I think I'm gonna add probably 3 or 4 cadence tutorials for you guys, in addition to the electrical VLSI, which will be very beneficial. Okay. Let's finish all the electrical VLSI labs first. See you guys tomorrow